Welcome everyone. My name is Nguyen Tran. I'm from Phenica University, Vietnam. Today I will be presenting a novel approach to antenna design for unmanned aerial vehicles based on the collaborative research between Phenica University, Vietnam, University of Glasgow, United Kingdom and Dongguk University, Korea. In this study, we will explore how their compact, dual circularly polarized antenna addresses the communication challenges in modern UAV systems. In this presentation, I will systematically cover the conceptualization, design, and validation of our proposed antenna. First, we will examine the stringent operational requirements of unmanned aerial vehicles and the inherent limitations of current conventional antenna geometries. Next, I will detail our specific miniaturization strategy utilizing coupled capacitive gaps. Following the structural overview, we will review the feeding network that enables dual circular polarization. Finally, I will present the simulated impedance, gain, and radiation parameters to formally validate the performance. Let us begin by establishing the operational requirements for antennas deployed on unmanned aerial platforms. Unmanned aerial vehicles operate in continuous motion, frequently altering their pitch, roll, and yaw during standard flight operations. This dynamic orientation introduces significant polarization mismatch when communicating with stationary or tracking ground stations. Implementing circular polarization effectively mitigates these mismatch issues and reduces the multipath fading that is typical in complex outdoor environments. Furthermore, upgrading to a dual circularly polarized system provides necessary polarization diversity. This diversity serves as a critical redundancy layer, substantially increasing the overall stability of the communication link. While the benefits of dual circular polarization are clear, integrating these systems onto small aircraft introduces significant physical challenges. The primary engineering challenge lies in the strict payload and aerodynamic constraints of modern drone platforms. For standard operation, conventional circularly polarized patch antennas must be engineered to a half wavelength. At sub-6 GHz frequencies, this half wavelength dimension results in a structure that is physically bulky and difficult to integrate smoothly into a compact airframe. While previous research has successfully shrunk patch sizes using various metamaterial or fractal techniques, those resulting designs predominantly support only a single polarization state, thereby sacrificing the critical advantage of polarization diversity. To resolve this specific trade-off between physical size and polarization capability, we developed a novel antenna configuration. Our proposed configuration is a miniaturized antenna with dual circular polarization, tuned precisely for the 5.6 GHz communication band. The primary objective was to deliver a compact footprint without degrading the fundamental radiation characteristics necessary for flight operations. As presented on the slide, the overall electrical size of the simulated prototype is extremely small, measuring just 0.18 by 0.18 by 0.04 lambda. Achieving this degree of miniaturization while maintaining structural simplicity and high inter-port isolation required a fundamental adjustment to the radiating patch. You can observe this physical adjustment by analyzing the specific geometry and material composition of the antenna. The physical architecture of our proposed antenna is highly layered. The primary radiator is constructed on a single sheet of taconic RF35 substrate, which is characterized by a dielectric constant of 3.5. The overall lateral dimensions are remarkably compact, measuring exactly 30 by 30 millimeters. To efficiently manage the signal routing without expanding the primary substrate footprint, the feeding network is physically separated. It is implemented directly below the main layer on an independent FR4 substrate, characterized by a dielectric constant of 4.4. The most critical feature of this geometry is the segmented nature of the square patch, which directly drives the miniaturization. To achieve the target electrical size at 5.6 GHz, we modified the conventional continuous metal patch. The square radiator is strategically divided into multiple distinct segments. This division introduces a series of narrow, coupled gaps across the radiating surface. In electromagnetic terms, these physical gaps act as supplementary capacitive elements integrated directly into the resonator. By loading the patch with this additional capacitance, we significantly lower the fundamental resonant frequency of the structure. This mechanism is exactly what allows the physical dimensions to remain so compact. Next step was establishing the dual polarization states. Generating two distinct circular polarizations from a single miniaturized patch requires precise feed placement. The antenna is sequentially fed at specific locations using the underlying microstrip lines. We utilize orthogonal probe feeds designed to deliver equal signal amplitudes coupled with a precise 90-degree phase offset. The routing dictates the polarization state. Specifically, transmitting a signal through the port designated as port 1 establishes left-hand circular polarization as the dominant mode. Conversely, isolating the signal through port 2 yields right-hand circular polarization. Implementing two ports on a highly compact patch typically causes severe interference. However, our simulation results demonstrate excellent port isolation. A known limitation in the literature is that utilizing a conventional asymmetrical patch for both right and left-hand polarization generally results in significantly degraded isolation between the ports. However, the plotted S parameters for our design validate its stability. The design features a satisfactory 10 decibel impedance matching bandwidth around our center frequency. More importantly, the interport isolation is maintained above 10 decibels throughout the critical 5.57 to 5.65 GHz range. The isolation performance actually peaks at an impressive 31 decibels exactly at 5.61 GHz. This robust isolation directly overlaps with our required axial ratio bandwidth and operational gain. For circular polarization to be considered pure, the axial ratio must remain below 3 decibels. Our simulations confirm that the 3 decibel axial ratio bandwidth spans from 5.52 to 5.66 GHz. Crucially, this span completely overlaps with the isolation bandwidth we just reviewed, ensuring a stable common operating band. Within this verified functional range, the broadside realized gain performs consistently, measuring between 2.4 and 3.4 dBi. The antenna ultimately achieves a maximum peak realized gain of 3.6 dBi, which is highly efficient given its minimal footprint. To physically verify how this gain is being generated, we must analyze the surface current distributions on the radiator. Despite the substantial reduction in the physical aperture size, total radiation efficiency remains above 50% across the band. We validate the polarization mechanics by mapping the surface current distributions at 5.6 GHz. The vectors distinctly show two orthogonal current components existing with a 90-degree phase difference. Depending on which port is excited, the resulting combined current vectors physically rotate in completely opposite directions across the patch segments. This physical rotation confirms the successful, independent generation of both right-hand and left-hand circular polarization states. Finally, we evaluate the spatial distribution of the transmitted signal through the simulated radiation patterns. The simulated far-field radiation pattern validates the practical utility of the antenna. Under standard excitation, the structure produces a highly symmetric spatial radiation pattern. A critical metric for dual polarized systems is polarization discrimination, ensuring the left-hand signal does not interfere with the right-hand signal. Our design achieves exceptional discrimination, showing a cross-polarization suppression of approximately 27 decibels in the direct broadside direction. Additionally, the structure directs power efficiently upward, maintaining a solid front-to-back ratio strictly greater than 13 decibels. To conclude, we have successfully developed and validated a compact dual circularly polarized antenna engineered specifically for 5.6 GHz unmanned aerial vehicle communications. By integrating capacitive gaps into the square patch, we resolve the severe size constraints inherent to standard half-wavelength designs. Simultaneously, the application of orthogonal probe feeds guarantees the independent generation of both polarization states. The resulting architecture maintains symmetric radiation, high interport isolation, and stable gain within a fraction of the standard physical footprint, proving its viability for modern drone integration.